So, today we're looking at other types of probability, so more sort of specific types. And think about the word discrete. When we learned about that back in Math 10, we learned discrete and continuous when we were talking about relations. Okay? Discrete means you can't have part of a value. Like you could have decimals, but you can't have an infinite number. Think about the real numbers. Between 1 and 2, there's an infinite number of numbers between those. Right? You can have decimal places to the billion, trillion, whatever in between. It's continuous. So, in this case, we're looking at things where it's right or wrong, or it happens or it doesn't happen. Okay, so in experiments, data is often collected in numerical form. For instance, 3 coins are tossed and the number of heads showing is recorded. We say the number of heads is a random variable, because it happens randomly, you don't know what it's going to be. And that it has possible values, so we're talking about the number of heads. That's the event. So when you're tossing 3 coins, how many heads could you get? You could get 1 head, right? 1 out of 3. You could get 2 out of the 3. You could get 3 out of the 3. Separate way, all the way back there. And then, or you could have 0. Right? You toss 3 coins, they might all be tails. So there's actually 4 possible outcomes for tossing 3 coins and looking for the number of heads. Another example of a random variable is the volume of water in a 50-liter rain barrel. You don't really know how much it's going to rain, right? So it could fill up in a day and be 20.23 whatever milliliters. It could be 42.1873 if you had the accurate enough to measure it that way. So that has possible values between 0, so we'll call it the volume, and 50. Once it hits 50, it overflows, right? So it can't measure it anymore. So in that case, that would be continuous. Is it some decimal value, perhaps, between anything, 0 and 50. So random variable x represents, in number form, the possible outcomes that can occur for some random experiment. When x equals the number of heads showing, the x has possible values 0, 1, 2, 3. We say that the number of heads showing is a discrete random variable because its possible outcomes are a subset of the set of whole numbers. A discrete random variable x has possible whole number values. X, that is, remember in IB, whole numbers is n. Number of agitation, n is natural numbers. So, just remember that. We're talking about whole numbers because we could have 0, right? A continuous random variable x has possible real number values in some interval. That is, x is a range of all real values between 2 boundaries. So the rain barrel between 0 and 50. Yep. Okay, so if x is the quantity of fat in a T-bone steak, then x is, you think that's discrete or continuous? Continuous, yeah. It could be, if you have the precise measurements, it could be any decimal value in between. If x is the number of hairs on your cat, then you can't have half a hair. Like, there's no size to it or whatever, so that is discrete. You have a hair or you don't. So you have 1 million hairs or you have 900 hairs, but you don't have 900.2 hairs. Okay? So that's the difference between discrete and continuous. Right now we're going to look at discrete in more detail, take math 35, you're going to look at continuous in more detail then. Okay? So if you're doing HL. So probability distribution of a discrete random variable can be given in table form, graphical form, or function form. So example 1, consider the experiment of tossing a coin 3 times in succession. List all possible outcomes. So 3 coins, what can you get? You can do a tree diagram or you can just start listing them. So first coin could be heads or tails. Second could be heads or tails. Third could be heads or tails. Okay, so what do you get? If I write it out, 3 heads, 2 heads, and then tails. Heads, tails, heads. Heads, tails, tails. And then from the other one, tails, heads, heads. Tail, tail, tail. Okay. Yeah. Just pause everything here. Okay. Right. So those are your possible outcomes when you're tossing 3 coins. So if the event you're wanting is the number of heads observed, what's the possible values of x? So you could have no heads, that would be x equals 0. Right? 1 head, 2 heads, 3 heads. Okay? That's for this particular experiment. We're looking for the number of heads. You can look for the number of tails. Obviously, it would be very similar values, right? Just use one or the other. Okay, and then think about the probability. So there's 8 possible outcomes here, right? Probability of getting 0 heads, that's just one of those possible. So that's 1 out of 8. Okay. Probability of getting 1 head, well, that would be this one, and this one. So 3 out of 8. Remember, this is theoretical probability. You're not actually tossing it. This is what would happen if you did this experiment a million times. Probability of 2 heads. Count them up. 2 there, 2 there, and 2 there. 3 out of 8. Probability of 3 heads, just 1 out of 8. Okay. So why is this considered a discrete random variable? Can you toss a coin or toss 3 coins and get 1.5 heads? No. I guess like the odd time it might land on its side, but you would do a retoss. Just like when they toss a coin at the start of the game. If it lands like that, they retoss it, right? So this is discrete because you can't toss part of. Okay. So we talked about how to display probability distributions in a table. Here's your x values. So for 0 heads, the probability is 1/8. We got that. We filled it in for you. For 1 head, it's 3/8. For 2 heads, it's 3/8. And for 3 heads, it's 1/8. Okay. So those probabilities, in this case, 1/8 is the smallest, 3/8 is the biggest. But for any probability, can't have a negative probability, so it's got to be greater than or equal to 0 and less than or equal to 1. Question?
How is probability of 1 head 3 out of 8? Because would it be like only just 1 head, or if you count?
Yeah, exactly 1 head. So there's 1 head there, 1 head there, and 1 head there. 3 out of 8.
3 heads is 3 out of 8.
Yep. three out of eight. No, for two heads, that's this one, and this one.
Oh, okay.
Yeah. So this is for exactly this number of heads. Okay, so the sum of all the probabilities, if you find all the probabilities in the entire set of possible outcomes, the total should be 1. Okay, we can add those together. 1 plus 3 plus 3 plus 1 is 8. Out of 8 is 1. Okay. So you can then use summation notation to show total probability. Okay, so this is just a repeat here of what we just did. In any probability distribution, if P1 is the probability of an event, then it's between 0 and 1. The sum of all the probabilities is 1. So really, we can use summation notation. We've already learned that. Hey, are you following? So draw probability distribution spike graph and histogram. So what's a spike graph? You actually draw a spike, a line with the dot on top, a dot on top. So in this case, our possible outcomes actually are numbers from 0 to 1. So often we would start 0 here, but because it's a spike graph and it's discrete, we can actually start away from the y-axis. You can put it on the y-axis, the vertical axis if you want. But those are the number of heads. Okay, and then this is the probability. Okay. I'm going to try, so use a straight edge if you have one. And so the probability, I should do that. So the scale needs to be an equal scale. So because we know it's out of 8, 1/8 or 3/8 are basically are two of our answers, let's make each grid marking 1/8. So this one actually I should show is 1/4 here. So I want to reduce. Okay, so make sure your scale is equal. So each grid there is worth 1/8. That's 2/8, 3/8. So now when I do my spike, so here up to 1/8, here up to 3/8, here up to 3/8, here up to 1/8. Not too bad, it's a little bit. Put maybe easier on your own paper. Yeah. Okay, and often we just distinguish it with so a dot up there. So we make sure it's easy to see what it is. It gives it a bit obviously easier. Let's call this spike graph. Okay, histogram. Same thing, except the histogram is bars, right? Join. So I would start 0 here. 1, 2, 3, 4. Well, actually, I'm going to label these spaces. Okay, because it is discrete. So these are going to be different. There's not values in between, so I can label between there, kind of like more like a bar graph, although they do call it a probability histogram. But then I think we did one of these earlier, right? Because I remember trying to do a nice rectangle. That's pretty good. So the scale is going to be the same. And I can actually use that one. And obviously, 4. And this is probability. 1, 8, 1, 4, 1, 8. Okay, next part. We are not doing this. Okay? So we have, in order to use a formula like that, you need to learn a little bit more, which you're going to do in 30-1. So we're going to leave that. Okay? Example 2. Explain why each of the following are not probability distributions. Okay, so take a look at them. Why do you think? You don't know what they're representing. But first one, part A, why do you think that's not a probability distribution? Correct. We add all of these up. We add up to 1.4, which is greater than 1. Okay. Next one, there's a formula for calculating the probability here. So if x equals little x, where little x is 0, or 1, or 2, or 3, this formula will give us the probability. So that means probability of x equals 0 will be 1 over 0 plus 2, which is 1/2. Probability of x equals 1 will be 1 over 1 plus 2, which is 1/3. Put a space here. Probability of x equals 2. 1 over 2 plus 2 is 1/4. Probability of x equals 3 is 1 over 3 plus 2 is 1/5. You add those together, you get more than 1, right? So common denominator would be what? 2, 6, 12, 60. So that'll be 30, plus 20 is 50, plus 15 is 65, plus 12 is 70 something over 60. So again, greater than 1, therefore not probability distribution. And what's weird about C? Negative probability. So can't have negative probability. Okay, so maybe P actually something else, right? But not probability. Okay, now the next one says determine K for that probability distribution. So you are told that it is a probability distribution, and you need to figure out what K is. Okay, and then determine what K of 3 is. So that means the sum of every probability for when x is 1, 2, and 3 has to equal 1. Okay, and then you can solve for K. Okay, so find the probabilities in terms of K. You're told it's a probability distribution, so that means they have to add to 1. So then you can work backwards to solve for K. Okay, alrighty. So, next part is what we call expected value. Sometimes it's called the mean value. So turn over to the next slide. Again, for a random variable. And so this is more basically using the theoretical probability to expect what would happen if you perform the experiment 120 times first time, or whatever situation it might be. So using the theoretical to figure out what would happen, not that you're actually going to do the experiment, but if you did. So a die is to be rolled 120 times. On how many occasions would you expect the result to be a 6? So based on the theoretical probability, so we're talking about a normal die that you've played board games with. It has 6 sides. So probability of rolling a 6 is actually 1/6. Okay? So 6s don't line up. If I said probability of rolling a 4, it would still be 1/6. It's the shape of the die, right? It's a cube. On how many occasions would you expect the result to be a 6 if you rolled it 120 times? What do you think you would do? Exactly. And we use a capital E. So expected value of 6 is going to be 1/6 times 120, or 120 times 1/6. So you would expect 20 rolls of 6. Okay. Might not be if you did that experiment, but theoretically that's what it should be. Okay. Next one, each time a soccer player kicks for a goal, she has a 75% chance of being successful. In a particular game, she has 12 kicks. How many goals do you expect she would get? Okay. So in this case, probability of, expected goals, in this case, we would have the probability is 75%, so that's 0.75 as a decimal, or 3/4 as a fraction, times 12 kicks. So that would be, what, 8? No, that would be 9. Okay. Will that happen? Not necessarily, right? But that's what the expected value. And that's why it's sometimes called the mean value, because on average, every 12 kicks she has, she should get 9 in, based on this probability that scoring that she has. Okay, in a factory, they test things that they make. They do a sample, a random test, to figure out how many things are coming out defective, so they know whether they have to fix the machine or whatever that's making them. So in this case, light bulb factory, they find that the probability of a light bulb being defective is 0.03. There's 120 light bulbs in the case. How many would you expect to be defective? Well, would be probability times however many there are. So what's that? 360, that would be 3.6, right? So basically about 4 defective. But we would leave it as a decimal, even though you can't have part of a light bulb. When they do their calculations at a factory, they would keep it as a decimal, so that they have the accurate amount. So you're always, to get expected value, multiplying the probability by the number of trials that you're taking. Okay. So in general, if the probability of an event is t, then the expected number of occurrences of this event in n trials is nt, or tn. Okay. The binomial experiment is repeated n times, and a particular outcome has a probability of p of occurring each time, then our expectation is that the mean, which is also sometimes this symbol mu is used, is np, or expected value of that event is np. Now this, what does it mean by binomial experiment? We'll get more into that in Math 30. Okay, just think about it as an experiment. What it means by binomial experiment is that there's only two things that can happen. It can happen, you can score a goal, or not score a goal. The light bulb can be defective or not defective. There's no in between, so two possible outcomes. Binomial means two, okay? But don't worry about that word right now. Just in terms of expected value, you multiply the probability of it happening by how many times your experiment is occurring. Okay? Okay, so in this case, in this game, the game of chance, the player spins a round spinner, labeled 1, 2, 3, 4. So you probably played board games with spinners. Okay, you spin it around, and where you land, usually they're colored. That tells you what box to go to, or maybe they're numbered. It tells you how many spaces to move. If it's a fair spinner, then these parts are all equal. Okay, if you want to make up your own game and rig it a little bit, then you make some of these a different size, so there's less probability, right? But you don't tell anyone, right? So we're assuming a fair spinner. So 4 equal parts. If it lands on spin number 1, you get $6. If it lands on spin number 2, you get $3. Spin part 3, you get $1. On part 4, you get nothing. So it's kind of like a game at Stampede or something like that. If you usually those games at Stampede or any carnival is really hard to win. Okay, they make it. In any case, so they might have this rigged a little bit without anything. So, assuming the likelihood of spinning the 1, 2, 3, or 4 are all equal, so those are all equal parts, then determine the average winning on a single spin. This is called the expected value of the winnings of a single spin. So, this is where the word mean comes in. On average, how much would you win? Well, what's the probability of spinning a 1? In this spinner, it's 1/4. Probability of a 2 is 1/4. A 3 is 1/4. A 4 is 1/4. Okay, so you really have to get the probabilities. They weren't given to you in that chart. Okay. Then, so the probability of spinning a 1 is 1/4. If you do that, you win $6. So the expected value of the game will be 1/4 times 6 plus probability of this happening. Spinning a 2, you win $3. Spinning a 3, you win $1. And spinning a 4, you win 0. Right? So you calculate each individual expected value and add them together. if you just took the average of all of these, would you get the same thing? That would be 9, 10, right? Okay, but let's wait till we actually get there. Okay, so calculate that. So they all have a denominator of 4. So that's going to be 6 plus 3 plus 1. So that's 10 out of 4, which is $2.50. Right? This is money. Okay. Because the spinner is equally cut into 4 pieces, you can add these up and then divide by 4. Find the mean of these. Okay? But let's say I made this a little bit bigger, so probability of spinning on a tube was higher and this was lower. Then you couldn't just add these up and divide by 4 because they're not equal probabilities. So that's why we're doing it the long way like this. Okay? So on average in this game, you're going to win $2.50. Nothing's free in this world. If they charge you $3, is this a good game to play? No. Okay? When you get old enough to gamble and maybe go to Las Vegas, you'll hear the term, the house always wins. The house is the casino. Okay? They don't play games that have an expected value where it's going to be bigger than 50%, like half the time, right? They want the house to win more than half the time, okay? But they need to make money, or they want to make money off of it. Obviously, you might spin this and get 6. You might spin it and get 6. You might spin it and get 6. But then spin another 100 times and get 0, right? So this is the theoretical value that you would get if you played this infinite number of times. Okay? So this is not a good game. Now is the cost to play is higher than the expected value. All right, so then again in summation notation, it's given to you in the box at the bottom. As I said, expected value, also the mean of a random variable, is given by multiplying that outcome by the probability, okay, for each possible outcome. So x1 represents a particular outcome, q1 is the related probability to that, and x is the random variable for the situation overall. Okay? When you get to studying for your IB exams, you'll get a data booklet, and this will be more what it'll look like. So they're not going to show the little bit of, well, actually, they might do both now. Show the PI there. Well, that's just this. Okay? This is the sort of IB notation. So take a look at example 4. Think about what you would do there. So it says store owner has determined the probability of a customer buying magazines. The data is shown in the table. So the probability of a customer buying 0 magazines is 0.1. 1 magazine is 0.23. 2 magazines is 0.28. 3 magazines, etc. Okay, first of all, so we're assuming here there's nothing, no other cases there. So is it a probability distribution? And they've given you all the information. Add up the probabilities. Does it equal 1? determine the mean number of magazines a customer will buy. So that's where, so mean number is the same as expected value. So that's going to be 0 times 0. Actually, I'll put the yeah, I'll put n times the probability. So that's 1 times 0.23 plus 2 times 0.28 plus 2 times 0.21. And then do that calculation. Obviously, this is 0. You've got a value for that. Enter it in your calculator. Anyone? Keep going, why not? Good. These days, I don't think people buy many magazines, but you go to the checkout counter, you always see magazines there. They're hoping for that last minute random buy when you're at the checkout. Okay. So that's it for today. There are exercises there. Flip over to the back of that page, say continue, and the answers are there as well. Okay? And then, you're still recording.